Speaker today is Professor Christian Wüthrich from University of Geneva, and he's also visiting professor at the Università della Svizzera Italiana in Lugano. He has several degrees in physics from the University of Bern and in history and philosophy of science from the University of Cambridge, as well as in philosophy from the University of Pittsburgh. He obtained his PhD in history and philosophy of science at the University of Pittsburgh afterwards. And since then, he conducted various research stays, for example, at Parameter Institute in Canada, Center of Theoretical Physics in Marseille, the University of Tübingen, and the University of California, San Diego. He received an impressive list of prizes and grants, just to mention one more recent one from the John Templeton Foundation for research collaboration between the University of Illinois, Chicago, and the University of Geneva. So by training, he's both physicist and philosopher, and his research therefore is on the field of philosophy of physics, with a more current focus on philosophical foundations of quantum gravity. And today he will talk about beyond the limits of analog experiments. We are very happy that you accepted our invitation and are looking forward to your talk. Thank you very much.
Thank you very much, and thank you very much for the invitation, which I very gladly accepted. As you correctly said, I'm by training, I'm both a philosopher and a physicist, but for the last quite a few years now, I've worked mainly as a philosopher. I do philosophy of physics, so I look closely at what physicists do, but what I consider myself be doing is not contributing to physics research per se, but instead of sort of reflecting on what's going on in physics with sort of more philosophically interested questions. And I'm going to present one such set of considerations concerning, you could say, the epistemology of scientific experiments, and the methodology concerning, in particular, the case of black hole thermodynamics. That's the focus today. So black hole thermodynamics is a hypothesis you could sort of summarize as asserting that black holes are thermodynamic objects. They have a temperature, they have an entropy, they radiate through Hawking radiation. I probably don't need to explain much what this is with this audience, I assume, but just to repeat two important points. They have an entropy which can be calculated according to the so-called Bekenstein-Hawking formula, and the important aspect of this is that the entropy is proportional to the area of the event horizon. In 1975, Hawking published the paper, that's the reference up here, where he presented a calculation which showed that in the presence of a black hole, that the quantum field theoretic vacuum state is in a thermal state, that is, it radiates as seen from infinity, asymptotic infinity, at a certain temperature, which is inversely proportional to the mass of the black hole. So in short, Hawking radiation is a black body radiation of a black hole at a temperature, temperature T, as seen as in infinity. Good. Now, although black hole thermodynamics as a whole field with all laws of black hole thermodynamics and all the different aspects has a surprising, really remarkable degree of coherence with established physics, and which is why I think almost all physicists, at least those physicists I talk to, are convinced that black holes are thermodynamic objects. But it needs to be said that the central thesis of black hole thermodynamics are not empirically confirmed. These are theoretical experiments, theoretical considerations and arguments which have convinced physicists that black holes are thermodynamic objects. These are not empirical results. There are some arguments which Bekenstein, when he started to develop black hole thermodynamics in the early 1970s, he produced some arguments based on information theoretic considerations and certain thought experiments, what would happen if you would, there would be such and such a process if you would drop an entropy package into a black hole and things like that. And by using all sorts of arguments like this, he tried to argue that black holes have an entropy. But most physicists didn't really take this original argument very seriously. Nobody really believed that black holes are thermodynamic objects until the 1975 article by Hawking. Hawking himself, in fact, was motivated to do that calculation in order to show that black holes couldn't possibly be thermodynamic objects. And then he got a result which surprised himself and which convinced himself that these are, in fact, thermodynamic objects. So the fact that black holes can radiate, which classically, of course, they cannot as perfect absorbers, means they can equilibrate, they can show thermodynamic behavior like ordinary thermodynamic objects or systems. And as Raphael Sorkin has said, I think capturing what many physicists believe to be the case, Hawking radiation is really the best known piece of evidence for the association of horizon area with entropy and for black hole thermodynamics in general. So the question then is, if black hole radiation or Hawking radiation is so central to the whole idea of black hole thermodynamics, is, could there be some sort of empirical confirmation of Hawking radiation rather than just theoretical arguments and considerations? If we could measure, if we could detect Hawking radiation, that would give us a very convincing confirmation of this whole sort of complex of ideas. Now, the problem, as I'm sure you're aware, is that it's not detectable in practice, at least not for astrophysical black holes, because the temperature of the radiation we would have to detect for solar mass black holes is about 10 to the minus 8, 10 to the minus 7, perhaps Kelvin or something of that order. And for supermassive black holes of the kind that we would expect them at the center of galaxies, it's even much less. It's 10 to the minus 14 or somewhere around there because they're very massive. Now, the problem, of course, is that these are tiny, tiny temperatures that we could not possibly detect against the natural fluctuations of the microwave, the cosmic microwave background. So that's not really an option for detecting Hawking radiation. So 40 years ago, Bill Unruh therefore proposed an intriguing idea that instead we should be looking at so-called analog systems. We could think we should come up with physical systems which essentially show the same physics, at least in some sense, as black holes, and we should use those systems to perform experiments on it to make observations. So if you think, for instance, of a fluid, that was the one of the original proposals of a fluid flowing in flux, then you have, as for instance, the fluid accelerates towards like something like a waterfall, then at some point the speed of the fluid will reach what is the speed of propagation of sound in that medium, and by that it would create a horizon. So if a fish would be swimming downstream along with that flowing fluid, at some point the fish could not emit sound waves or sound signals anymore that could be received by the asymptotic companion fish that could detect these signals. Now, there are many other such systems, it turns out, where we could have something like that, something like event horizons present, in particular also in Bose-Einstein condensates. And 5 years ago, Jeff Steinhauer in Israel has published an article where he described how he has detected Hawking radiation in a Bose-Einstein condensate. As far as I know, this is not a result that's been reproduced by other groups elsewhere, but it remains, it opens, at least from a philosophical point of view, an intriguing possibility, namely that we could considered the detection of Hawking radiation in these analog systems as a confirmation of Hawking radiation in astrophysical black holes. The idea, of course, of this analog form of reasoning is that if two systems are known to be similar in some relevant respects, then we're also justified in thinking that they're similar in some unknown respects. So if we think that the physics for the black hole and the analog system is somewhat relevantly the same, and we would detect in one case Hawking radiation, then we would infer that in the other case there should be Hawking radiation as well. So the central question is, can analog models confirm gravitational Hawking radiation? Can we learn anything about black holes from these analog models? And more generally, can analog models confirm hypotheses regarding inaccessible target systems? Because one problem, of course, is that an astrophysical black hole is not accessible in the same way as an experimental system is in terrestrial physics. Now, interestingly, almost 4 years ago, Radin Dardashti, Karin Thébault, and Eric Winsberg published an article where they said that analog experiments can, in fact, yield such a confirmation. In fact, they give us reason to believe in a particular hypothesis about the systems that they're supposed to represent, or as it's said in the literature, about the target system. That is the system that is really the target of your interest. In our case, black holes. And they offered an in-depth study of analog gravity and how it can confirm gravitational or astrophysical Hawking radiation. The idea can be expressed in this sort of systematic figure here. So the target system is the black hole. That's what we're really interested in. And the question is, do black holes emit Hawking radiation? That's what we would like to detect. That's what we would like to confirm in empirical ways. Of course, we have a model, a mathematical model that describes the black hole, that represents the phenomenon that we're interested in. The idea is now that we have here a right-hand side which exactly mirrors the situation with black holes. We have some analog system, a Bose-Einstein condensate or some sort of hydrodynamical system, which is of course also described by a mathematical model describing the physics that's going on in this analog system. And if we now detect Hawking radiation in this analog system, the idea would be that this confirms the Hawking radiation over here. Now, for this inference to work, Dardashti, Thébault, and Winsberg argue that we need to establish the external validity of this experiment on the right-hand side here. And establishing the external validity, that is, to sort of make an inference from the experimental system beyond to the target system, we need to have two things in place. First is what they call a syntactic isomorphism. That's a relatively straightforward step in the sense that what we need is basically the same mathematical description here of the relevant physics. That's the sense in which they have to isomorphic. So the mathematics used to describe the black hole here, or the radiation here, has to be the same, relevantly the same as on that side. And this can be shown to be the case. In fact, this was already to some degree established by Bill Unruh 40 years ago. This is interesting, this is intriguing, that the same mathematics can be used to describe the physics in these two cases. But if it's just the mathematics, then it's a formal analogy, which we do not know whether it has some physical relevance, whether the physics is also relevantly the same. Because we know that sometimes mathematics can be, the same mathematics can be used to describe very different physics or different systems. For instance, the Lotka-Volterra model of predator and prey populations is a very, very general mathematical model that can be used to describe the behavior of systems which are very, very different, and we would think have nothing to do with one another. So the question is, to what extent does this formal analogy now really should tell us something about the physics. And for this, we need the second condition here, which is the idea of adequacy conditions. In other words, what we need to make sure is that in both cases, on the left and the right-hand side, this representation relation here between the model and the physical system is adequate. This is meaning that the mathematics we use really adequately and relevantly describes the physics that's going on here. And we need to do this on both sides, of course. Now, for this, in their argument, DTW, Wüthrich, Thébault, and Winsberg make two assumptions, namely that for certain purposes and to a certain degree of desired accuracy, I mean, these are all at some level approximations, of course. The modeling framework MS, that is the modeling framework used to describe the analog system, is adequate for modeling the analog system within a certain domain of conditions. And we need to make exactly the same assumption about the black hole. So we need to assume that the modeling framework for the black hole is adequate for modeling black hole physics. Now, if these adequacy conditions are successfully established, they would tell us that it's not just a formal sort of analogy, it's not just a mathematical coincidence that we use the same mathematics to describe. This really gets the relevant physics exactly right in both cases, and so the physics must be, in some sense at least, the same. Now, of course, if you look at step 2 here, they are assuming that black holes are accurately described by the modeling framework from which Hawking radiation is derived. That's one assumption that needs to be made. In other words, this here is an analogy that needs to be presupposed. This is, the same over here as well. Okay. Now, I'm not going to read that quote, but they just tell us what that means or why they're confident in doing that. Very briefly, what they have is they say we have a fixed classical spacetime that features the establishment of an event horizon via gravitational collapse, normally leading to a black hole. And secondly, we have a quantum scalar field evaluated in the regions of past and future null infinity, which are assumed to be Minkowski. Now, what you need to make sure actually is, sorry, the typo here is that you can deal with the so-called trans-Planckian model, problem, if you can convince yourself that there is no such problem of trans-Planckian physics, then you are somewhat confident that the modeling framework in the black hole is correct. Now, the problem is all of these arguments, also including the arguments trying to address the trans-Planckian problem, all of this work is theoretical. None of this is any empirical confirmation. But the problem with this is that it's not known if the particular modeling framework used in the derivation of Hawking radiation is actually describing black holes in the first place. That's in a way what we want to confirm. So we're not allowed to help ourselves to this assumption in the setup of the argument. That's the problem. Now, how could we convince ourselves that the modeling framework is correct? I see two ways. One is, of course, empirical confirmation in the usual way it's done in physics, or we would have a more fundamental theory of quantum gravity, for instance, which would underwrite the adequacy of the modeling framework and from which we could derive from more fundamental physics that there is, for instance, no trans-Planckian problem. Now, the problem is, because we don't have any empirical confirmation, that was precisely the reason, of course, why we wanted to do analog gravity. And unlike in the case of analog models, we don't know the correct theory of quantum gravity yet. We don't have a very good control of the fundamental physics on the left-hand side, as it were, on the side of the black holes. So in the analog cases, we do have fundamental theories. In fact, layers of fundamental theories. that you can go from approximations to a more precise and more rigorous and more fundamental description using sort of maybe molecular hydrodynamics or Lyubov, Bose-Einstein condensate theory, and ultimately, of course, some form of quantum field theory is going to describe the physics there. And you have a pretty good theoretical control over what you're doing, and you have ample empirical confirmation that this is the correct theoretical framework in which to analyze the physics. So we have very good, solid control, theoretically and experimentally, on the side of the analog physics. But of course, the problem is exactly that we do not have anything like that in the case of black hole physics. Okay. In a way, you can ask yourself, or you can say, the question is, what we would like to know is whether black holes fall in the same universality class as the analog systems that we're considering, that we're testing, that we're building in our physics labs. Same universality class, meaning that they show the same relevant behavior in this respect. And of course, if we would then find that all the other members, the terrestrial physical members of that universality class show or exhibit Hawking radiation, then we could be very confident that black holes do it as well. But of course, the question is precisely whether black holes fall into that universality class or not. That's really the question we would like to know the answer to, and we would like to have empirical confirmation for. So in sum, in a paper which is forthcoming, I concluded together with Karen Crowther and Niels Linnemann that by assuming that black holes are adequately described by the modeling framework from which the derivation of Hawking radiation is a necessary consequence, these authors already assumed the conclusion that they're trying to establish, namely that Hawking radiation exists in black holes. So it's in this sense that this is a circular form of confirmation. It's begging the question. So it's not giving us a sort of a new independent empirical confirmation. Now, you could argue, of course, against this and say, okay, maybe it's not confirmation we get, but surely we're learning something when we do analog gravity and when we test these things. And I would certainly agree that we learn quite a bit when we do analog gravity. Analog gravity is a fascinating area which has become a very active research area where we learn a lot about the physics of analogues of these analog systems. There's no doubt about that. But the question is, are we learning something about black holes? And you could say that, okay, what we get in the case of black holes is not confirmation. For that, we would indeed need direct empirical evidence from black holes, but surely it adds some plausibility. If we see the same thing happening with analog systems in terrestrial physics, then that makes it more plausible in some sense that black holes behave the same way. I have some reactions to this. Now, I'm not sure exactly what you mean by plausibility or what the opponent would mean by plausibility here. If they mean that analog gravity can deliver a proof of concept, namely that it's possible that, you know, or that it's even the case that the system described by these models does exhibit Hawking radiation, then that's fine. Absolutely, there's no question about that. So in that sense, yes, it adds plausibility. But it doesn't deliver confirmation. In other words, it doesn't tell us whether our belief that black holes are thermodynamics objects is true. That is not confirmed. Okay. How am I doing for time? Is it about 50 minutes?
Yeah,
sorry?
You're doing fine. In total, it's like 45 to 50 minutes. So you still have like 20 minutes at least.
Good, great. So let me quickly, in the second paper, let me quickly present the results of the second paper, where this is made more precise with a fourth author, Stefan Hartmann, what they mean by confirmation. And what they mean by confirmation is they use a Bayesian model. So they have a Bayesian network. They draw a Bayesian network. This is the Bayesian network that they draw. Now, I'm not sure how much you know about Bayesian networks, but these are variables or magnitudes or theses that are related in some sense with one another in a network of dependencies or relationships which are exhibited by these arrows. M, this node here, is the idea or the proposition that the modeling framework is an empirically adequate description of the physics of the target system, in our case of the black holes. That's M. A is the corresponding assumption that the modeling framework is empirically adequate for the analog system. Now, E is the evidence that we find, namely the detection of the Hawking radiation in the analog system. So suppose that is observed. Now, here, this X, that's sort of a universality assumption that the physics in M, or in this node here in the black hole case, and the physics in the analog gravity case is relevantly the same. Now, it is this parent node here. It's apparent because it has dependencies away from X to M and to A, which underwrites this universality claim. And if you accept that this is the Bayesian network of dependencies, then you can prove the following theorem. Assuming a positive probabilistic dependence for each of these three edges in the network, then you can show that the probability of M given E, conditional on E, is larger than the probability of M. So the probability that the modeling framework adequately represents around the physics of the target system in black holes increases if we conditionalize on the evidence E. In other words, it is confirming evidence. If we detect Hawking radiation in an analog model, then this confirms astrophysical Hawking radiation. Now, you need to make assumptions here. The positive probabilistic dependence, I'm not going to go into this in any detail, but you need to assume that given X, the probability of M is higher than it is given not X. So in other words, it's more likely the case that black holes behave in the way they do, given that they're part of the universality class than not. So this is what asserts the positive relevance for the universality argument for the target system. Now, the authors think that this is perfectly modest because by assuming such a connection, you don't, you're not thereby certain that the physics of the black hole is really like this, is adequately described by the modeling framework. The only thing what you need to assert is that it's the probability that this is the case is somewhere between 0 and 1, exclusive the boundaries. But connecting variables X and M in the graph, we already presuppose, even though in a probabilistic way, what we would like to establish, namely that black holes fall into that relevant universality class. Now, it may appear that this is a weak assumption because the only thing you need to assume is that this probability is not 0. It's nevertheless the case that if you accept this as correctly describing the situation, the Bayesian network that is, it's the case that you can do enough lab work on terrestrial systems such that you can virtually be certain that black holes emit Hawking radiation. You never, ever need to look at a black hole to get to any level of certainty to get that. That cannot possibly be right, it seems to us, because what we're precisely interested in is whether black holes are appropriately modeled. And it seems like even though we can get plausibility from doing terrestrial analog gravity, none of this can really make us, to any degree you desire, certain that this is in fact the case. Now, I have an analogy from philosophy of mind, which I'm going to skip, but if you're interested in philosophy of mind, I'll be happy to talk about this in Q&A. Now, that was the status of the debate until very recently. Now, just at the end of last year, Peter Evans and Thébault have published a paper in which they respond to the paper by Crowther, Linnemann, and myself. Even though it's not published yet, they respond to it. And here's what they say. Our second core claim is that an experiment of a manipulable and accessible source system of a given type, that is the kind of terrestrial analog system you have, that's manipulable because you can manipulate it, it's accessible, it's in your lab, and so on and so forth. So experimenting on a system like that can, in some circumstances, be used to make inductive inferences regarding a target system of a different type. In particular, when we have good reason to believe that the source and target phenomenon questions are universal, it is possible to make inductive inferences from the existence of the phenomena in the source system, so when we detect Hawking radiation in an analog system, to the existence of the phenomena in the target system, so that to the existence of Hawking radiation. Now, this they accept is a new form of intertype uniformity principle. That is, you have a principle according to which physical systems of different types nevertheless fall under the same universality class. Okay, and they think that this kind of assumption or principle is really similar to other uniformity principles that we accept. For instance, there's spatial uniformity principles, assuming that if you make a physical experiment of a certain kind, if you test something on an analog system in a physics lab in Geneva, you will get the same as you will in Trieste, for instance. So when you make some experiments in Trieste, you can make inferences how elsewhere in the world or in the universe this would look like. That's a sort of a spatial extrapolation, if you want. Of course, you can do the same thing time-wise. You could say that if we perform this experiment today, what we will see should give us some indication of what we would see were we to do it tomorrow. So that's a way of extrapolating in time. Space and time extrapolations are very common, of course, because we assume that the same laws of physics govern, at least for the most part, the relevant area of space-time. And of course, if we have one type of system, if we have a Bose-Einstein condensate and we make experiments on that, then we can also make an inference to all other Bose-Einstein condensates, to all other physical systems of the same kind. If we detect that a copper wire is a good conductor, then we can infer that copper in general, any wire made of copper is a good conductor. So it's an inference, an extrapolation to include all physical systems of the same kind. And now what they think is that this extrapolation to other kinds of system is really no different from those kind of extrapolations. Now, of course, the relevant question is whether this is a problematic inference or not. They go as far as to say that it would be as unreasonable to doubt a principle of extrapolation like that as it is unreasonable to doubt that the basic laws of nature will still be holding tomorrow. So that's the inductive skeptic, which some philosophers like to think about. But they also think that if somebody's an inductive skeptic, then you cannot do any science whatsoever because you're just not accepting the idea of extrapolating or assuming that the laws of nature have some form of globality. Okay, so we have inductions really of two kinds that are going to be relevant for us here. It's the inference from accessible to inaccessible systems, and the inference from intra-type, that is, of systems of the same type to systems of that type to systems of a different type. These are two different kinds of inductions that we're going to be interested in. And they give us a very nice example of a physical system or physical processes which are intra-type, so of the same type, but where we make inferences to inaccessible systems. And that's the case of stellar nucleosynthesis. So if you do astrophysics, main sequence stars, which is a class of stars which includes our sun, the theory, the accepted theory in astrophysics tells us that there are two principal reactions which transform hydrogen into helium. There's the so-called proton-proton chain and the so-called carbon-nitrogen-oxygen cycle. It doesn't matter what the details are of these two sort of processes which transform hydrogen into helium, but there are these two kinds. Now, what's common to both of them is that they take place deep in the core of the star, not on its sort of surface or anywhere near the surface. And the relative abundance of the two reactions depends on the size of the star. So there is in astrophysics, there's a rather detailed theory and understanding of this nucleosynthesis in stars. Now, clearly, both of these processes are unmanipulable. That is, they're not accessible to manipulation by experimental physicists because we cannot go to the interior of stars. And they're at least sort of visually, photonically inaccessible. That is, we cannot see them. In the visual frequencies, we cannot detect signals directly from these sort of reactions. However, and this is an important point, that doesn't mean that we cannot detect directly what's going on in the interior of stars. In fact, the neutrinos created in these reactions can be detected on Earth. Now, as Evans and Thébault rightly say, the inference from observed phenomena of the stellar surfaces, so the surfaces we can see, of course, and what's going on in interstellar space, that is in the space between the star and Earth, and of course from terrestrial physics. So we have a lot of knowledge about the spectra of terrestrial atomic systems, of nuclear phenomena. Physicists have 100 years or more experience of experimenting on systems like that. Now, given all of this, all of our knowledge of astrophysics, including astrophysical observations, but also, and very importantly, of course, particle physics, well-confirmed theories of particle physics, means that the theory of stellar nucleosynthesis is largely confirmed. That means they conclude that it's not the inaccessibility of a black hole in itself that makes it sort of not amenable to empirical verification. And I certainly agree with that. So it's not just the inaccessibility in itself that is problematic. There is, they say, prima facie, however, a fundamental difference between inference, that is, in the case of stellar nucleosynthesis and the astrophysical Hawking radiation, if one thinks that there is a fundamental difference in kind between the intra-type regularity principles, because it's the same type of physical systems that exist in the interior of a star. So the proton, the hydrogen, the helium, the protons, all these particles and atoms that we believe are present in the core of a star are, of course, of the same type than the protons and etc. on Earth. So in that sense, the intra-type regularity principles. And then, the astrophysical Hawking radiation is an inter-type regularity because a black hole is not the same thing or not a priori the same thing as a Bose-Einstein condensate. Okay. Now they say they find nothing special about inter-type inductive reasoning that bars inductive triangulation, the sort of inductive reasoning that we would have used, for instance, in the case of stellar nucleosynthesis. And they base this on two observations. First, they say that a lot of intra-type reasoning in science might be reinterpreted as inter-type reasoning in a given context, and they think of molecular, material science, life sciences. And it's true, sometimes what makes two systems of the same type or of different types can be reinterpreted depending on how you think of these different systems. And maybe once you come to understand that the relevant phenomena are the same in two cases, you may then have a good reason to actually subsume the two systems as of the same type, at least vis-a-vis a certain experimental or certain phenomena that you're interested in. So it's true, it's difficult, it turns out, to have a principled sort of firm distinction between these two cases. Moreover, there exist examples of scientists using Wilsonian type universality arguments to justify inter-type reasoning of this formula range of condensed matter context. So you can use arguments from physics established in condensed matter physics, for instance, where you have valid forms of reasoning from one type of system to another type of system. So you could summarize the situation as follows. You have the accessible systems and inferences of intertype. These are, of course, completely unproblematic. They're accessible anyway. If you don't believe me that this copper wire conducts as well as the other copper wire, it's accessible, it's there, test it, no problem, right? That's unproblematic. Now, there's one type of inference which uses those kind of insights to infer then to inaccessible systems. So if there is a copper wire on the back side of Jupiter, it's not really exactly accessible to us, but nevertheless, there's good reason to think that this is exactly of the same type, and therefore we could unproblematically assume that it conducts electricity. On the other hand, we have the inference to another system which may be prima facie of a different type, but it's accessible. I say that the physics here in this Bose-Einstein condensate is relevantly similar, of the same kind as in this hydrodynamical system, for instance. They're prima facie different types of systems, but both of them are accessible. If you don't believe me, you can always go and test the other system. So they're both accessible. Both of these are frequent ways in which we make inferences, we extrapolate, and they seem to be completely unproblematic. The question now is whether combining both of them, so you make an inference from something that is accessible of the same kind, now to something that's not accessible for empirical verification, and which is prima facie, at least of a different type. The question is whether that diagonal inference is in any way problematic. And Evans and Thébault think it isn't. One final option, of course, of interpreting our argument, they say, might be that there is an inferential problem specific to inferences based upon the combination of the two, so going along the diagonal. And this is exactly right. This is what we're trying to show, that this is dangerous and problematic. The idea might be that there's some problem inherent to this combined inference that is not reducible to either of its components. It is difficult, however, to see how the logic of such reasoning would work. If it is permissible to reason separately from accessible to inaccessible systems and from systems of one type to systems of another, then we need some reason why it is not permissible in principle to reason from accessible systems of one type to inaccessible systems of another type, so long as our inferences obey classical logic such as concatenation must be accepted. There seems no room for reasonable doubt. I think this is an extremely strong statement. I think there's no room for reasonable doubt that this is a valid inference. Now, I would certainly want to say that no, classical logic is not valid for such inferences. These are inductive inferences, not deductive ones. Maybe, given that you're scientists, you're not so much interested in logic here, but they misuse logic in that statement. But the problem is that the concatenation, the combination of an inference both to systems which are inaccessible and presumably of a different type is exactly what is problematic. And it's problematic if we think that this is an inference through which we can get a confirmation that the physics of this inaccessible physical system of a different type is the same. That's the problem. It's this combination of simultaneously inferring to an inaccessible system that is of a different type that makes the inference risky. Okay, so given the inaccessibility of the system, we cannot assume that it is of the relevantly same type, that is in the same universality class. For that, we would have to test it. And how, if it would be accessible, we could test it, and that would be no problem. If we have other reasons, like in the case of nucleosynthesis, to think that it's exactly of the same type, it's exactly the same kind of system, then that would be fine as well. But we don't have sufficient control for either of these inferences to work. So let me conclude. Now, an important thing is, if I've given talks about black hole thermodynamics to physicists, sometimes people have thought that I object to the idea that black holes are thermodynamic objects. This is not the case at all. I think with all we know, we have very good reason to think that they are thermodynamic objects. I'm not disputing this. My question is, how do we establish that? How can we learn or be sure, reasonably sure, that this is the case, that is in fact the case? And this, I think, is what's interesting and not trivial. So there are arguments, theoretical arguments and considerations you can make for black holes to be thermodynamic objects. Many of these are extremely suggestive, very suggestive, and it's, as I said already, it's remarkable the coherence with known physics that we find by assuming that black holes are thermodynamic objects. But this is not conclusive because, as I said, it lacks empirical confirmation. Now, for all its ingenuity, the argument that Thébault and collaborators in various papers have produced crucially begged the question by assuming what it is that we want to confirm. And of course, in that sense, it's a circular form of justification. Now, eventually, what we will need, of course, is we need firmer constraints on theorizing. So we need theoretical progress in quantum gravity, which may be eventually, of course, even be empirically confirmed, maybe in very different ways than detecting Hawking radiation, of course. And if we can have that, if we can get a theoretical framework, which is in itself confirmed more fundamentally, which tells us then that black holes are thermodynamic objects because, for instance, the Trans-Planckian problem dissolves or something like that, then that would be, of course, the kind of work that's needed. Or some sort of maybe very tiny black holes. If you can create tiny black holes in a lab, which then quickly evaporate because they're so tiny, of course, and you can detect the detection, that would be awesome. That would be certainly giving us confirmation that we're seeking. So in other words, what you need to do is you need to do astrophysics, you need to do quantum gravity, and in particular quantum gravity phenomenology. Thank you very much.
Okay, we thank you very much for this very, very nice talk to follow. Thank you. Now we have time for questions. I will look in the chat. If you want, you could just speak up or raise your hand.
Can I make a question?
Yes, sure.
Hi, I'm Stefano Liberati.
Yes, I think we've met at some point.
Yes, we did.
Yeah.
So thanks for the very interesting talk. So if I understand correctly, what you basically say is that there is a gap in the analogy in the sense that we understand fully the analog system. We have very much control about it. But what we miss is that to be sure that what we see in the sky, what we call black holes, are basically well described at the suitable approximations from GR plus quantum filtering curve space-time. Basically, they are really black hole. For example, they could be ultra-compact objects with a surface within the light ring supported by some kind of new physics. That is your objection. And by testing Hawking radiation in analog gravity, you cannot prove that it will be, you cannot apply the analogy in a straightforward way, because basically these objects, you don't know if basically, because normally the argument is that if they have the same mathematics, right? If I have quantum filter and a curved metric, the metric is describing an object with an horizon, then basically you can derive Hawking radiation. You don't need to know GR, you don't need to know what is the physics underlying the metric. Or if the scalar field propagating on it is a quasi-particle in a Bose-Einstein condensate, or is some photon in a curved background, you see? So if I understand, this is the crucial point of your criticism of the.
Yes.
Yeah.
Yes.
Now I have few comments from the side of someone making research from in this one. So I see your point, and I think it's pretty fair. I have one comment, which is maybe you may be interested to know that Steinauer did also the experiment in 2019 and 20. And now the evidence for the detection of Hawking radiation and the fact that there is a suitable regime, which is really described by the theory of Hawking radiation, that means quantum filtering curve space-time, that is very much confirmed. So, but that of course is perfectly fine for you, because it's just a confirmation that we understand very well the analog system, and that the analog black hole behaves as it is supposed to do by the theory of a quasi-particle on a Bose-Einstein condensate. That's what you would say, right? Now, another point is that in your presentation, you touched the Trans-Planckian problem, but I would like to stress that this was much more crucial in the analog gravity community than what it may seem from outside. In a certain sense, the focus of the community 20 years ago wasn't so much to prove that astrophysical black hole radiated by Hawking radiation. The proof, the really focus of the research was this. Even assuming quantum filtering curve space-time and the fact that astrophysics form black hole, that means object with an event horizon, still there was a fly in the ointment, which was the fact that the Hawking derivation seems to rely on a knowledge of the theory of space-time and quantum field theory at Trans-Planckian regimes. And so the point was, is the Hawking radiation derivation robust against the Trans-Planckian regime? Analog gravity provides a system where you know what is the Trans-Planckian regime, and you can prove within which approximation the Hawking radiation result, the temperature that you show, is confirmed, even if there is new physics at Trans-Planckian scale. In the case of condensed matter system, is basically the breakdown of Lorentz invariance, which then stem what you say quantum gravity phenomenology, all the quantum gravity phenomenology, or a good branch of it in testing Lorentz violation, came from part of the analog gravity community, myself as well. And then I have, sorry if I am making a long comment, but I just want to condense it. And another, so because you stimulated your talk, some thoughts that I think you may find interesting per se. And this is one thing that you see, for me, an extra criterion that make me think that if black hole forms in astrophysics, then they must be object is self-consistency, because general relativity predicts the 4 laws of black hole mechanics, Bardeen-Carter-Oak in 1973. If you apply those laws and you don't have the possibility of radiating, Hawking radiation, then you can lead to violation of the generalized second law. So to me, it seems that at least from internal consistency, general relativity must have some way to make black hole radiate, because otherwise it wouldn't be self-consistent. It's very amazing and tantalizing that you need quantum field theory to do this. But of course, you can say maybe in astrophysics, we don't form black holes. What we see in the sky are not black holes, are ultra-compact objects. My final comment is that, interestingly enough, analog gravity can even describe what happens if you have, for example, a forever collapsing object that never crossed the horizon. And you can simulate this kind of physics on an analog gravity model. So the analog gravity may have also the power to simulate situations which are not the standard one for which it was thought for. That means, for example, the black hole thermodynamics. And that is also something that might be interesting to explore. Thank you. Sorry for the long comment.
Yeah. Thank you very much. Let me react to some of what you said, if I may. So first of all, yes, I think, obviously, people experimentalists working in analog gravity will make progress, as Jack Steinhauer does, or maybe other groups as well. I don't follow day to day, the new results there. And if they find that certain assumptions, or that the modeling frameworks they're assuming is confirmed there, that there's no problem of trans-Planckian physics, all of these sort of things, that's fine. I think when we do that kind of research, we learn a lot about these analog systems. And in a way, it's a proof of concept in the sense that we know that we can do quantum field theory on something like curved spacetime with event horizons in a way that's coherent and in which can be resistant, as you said. I think that was your word, resists against trans-Planckian physics interfering.
Robustness, we call it
robustness, sorry, which is robust against trans-Planckian physics. Now, all of this is perfectly fine, but nevertheless, this is work done on analog systems. What is the guarantee, the empirical confirmation that black holes are behaving the same way? That's exactly the question. So, in a way, I think much of this work is extremely fascinating and important. It's very suggestive also. It's very plausible, giving a lot of plausibility. There's no doubt about that. With sort of coherence within known physics, I would say, different aspects, not just GR, but including quantum field theory as well, and that is impressive. Now, what should we think about the argument about? I think that was your third point about the internal consistency or coherence of the idea of black holes as we have it in GR. Now, it's true that the black hole thermodynamical laws are in perfect analogy with thermodynamical laws, and these are laws that we can find in pure classical GR. Now, of course, that would just be an interesting formal mathematical analogy if it weren't for the addition of quantum field theory, which we need to have so that black holes are not perfect absorbers, but are now objects which can radiate and equilibrate like thermodynamical systems do. So you need that. It's not GR in itself. It's GR and so some more, of course, well-established physics that you need for the coherence. Now, as I said, all of this is really remarkable. The level of coherence you get, it's super fascinating. It's very, very, very strong theoretical evidence to believe that that black holes are like this and are thermodynamic objects. I would grant that, absolutely. That's not the point. But these theoretical arguments, because as you yourself rightly pointed out, it could be that the objects that we now observe and believe to be black holes, and therefore well described by that modeling framework, may in fact not be correctly described by that modeling framework. They may be objects which are in some interesting sense different from what we thought they were. And how could we ever find out whether or not that's the case? Well, we need to look at the world, and we need somehow empirical confirmation of these ideas. And I think, my point is We will not get empirical confirmation of this idea by looking at terrestrial physics.
Yeah, but let me say this: if we will have uncontroversial evidence, and we may have it in the next decades, that the object in the sky have an horizon. Mm-hmm. So they are endowed with an horizon, and then I would say that we have tested the general relativity in regimes where we know basically that the description as a metric theory of gravitation is correct. And we know quantum field theory is correct in the regime in which we would be supposed to apply it close to the horizon of astrophysical black hole. You don't have quantum gravity regimes, right? So if you have the evidence that there is an horizon, you have basically no evidence to not trust that quantum field theory is okay there. Then these two ingredients together, basically by just consistency, you need to have Hawking radiation. Now Hawking radiation may be too cold to be tested. That's correct. The only way we could test Hawking radiation is to produce a micro black hole or find a natural micro black hole, which is extremely difficult. But still, in a sense, at that point, you are just testing. You are putting together two theories that you have tested in many different aspects in a regime where, at that point, you wouldn't have any reason to suspect that is wrong, except for the Transplanckian problem. But then you have already an independent derivation showing you that it doesn't matter the microphysics of the analog system, and the Transplanckian problem, really Hawking radiation is robust as long as the temperature of Hawking radiation is very separated from the microphysics scale. So basically you have a comparison of scale. If you have that separation of scale, the derivation is robust and it doesn't rely on whatever is underlying the space-time. So at that point, I would find very difficult. So my doubt, and why I in a sense pose your argument that we haven't proved yet that those objects with Hawking radiate, is that we don't understand yet those objects. We have to be fair that they really look and smell like a standard GR black holes, because we have now seen the shadow. But those are regime where we haven't probed the horizon. We have probed the light ring better. So we have probed an external region with respect to the horizon. But once we will have firmer evidence that these objects have an horizon, and we are getting there because there are ways to distinguish object with a surface from object with an horizon, albeit very difficult, probably more difficult than what people think now mainstreamly. Then I would say that it's very difficult to escape the conclusion that the Hawking radiation is a part of nature. Of astrophysics. It's just a very faint phenomenon that you will have to look in the different aspects to.
Yeah. Good. Thank you very much. Yes, I agree with that. So I think that's it's not necessary to have direct empirical handle on the robustness of a black hole against Transplanckian physics itself. It may be enough to have a direct observational evidence for other facts, and in particular, of course, the existence of a horizon, which is a necessary condition for deriving Hawking radiation. That would be strong empirical confirmation. I agree with that. Yes, but that is looking at the black hole itself and learning more about it. And once you do that, yes. And I'm very happy to hear. I mean, you're closer to this than I am. I'm very happy to hear that we may be getting close to getting that. But yeah, I mean, my point is, for this, you need to look at black holes, not at Bose-Einstein condensates in your lab.
Mm-hmm. Yes.
Okay, thank you very much. This was a very intense discussion now. Is there anyone with maybe a short question? Because we had not so many opportunities so far. Anyone? Okay, it seems not to be the case. Then, yeah, I thank you again.